So what I'm going to talk today is about resiliency of the power grid and how microgrid can help. Now, as we understand, resiliency means that even under extreme event, ability to supply load and as distributed resources we have in the system within the microgrid or outside the microgrid, how we can take the power from microgrid and supply to the critical loads. Now, microgrid is typically meant to supply the power within the microgrid, but you can also use the microgrid power just like a resource as a like a DER. If there is surplus power, if you manage within the microgrid well, to supply the power outside microgrid, right? And hence it can enhance resiliency inside and outside too. Now, of course, there are a lot of practical constraints that protection should support it, control should support it. Your network should support this, these kind of power flow from within the microgrid and outside the microgrid. And then ability to do prediction of anything that is caused by extreme event like hurricanes and storms is also very important, and using the microgrid resources to keep supplying the power, right? And form an island, which is microgrid is of course designed for, but microgrid with changing boundary, again, supporting protection and control is become important. So let me first start with, a little bit background. So if you look at over the years, especially last year and this year, there has been more and more extreme events. So starting with a different part of the world, here, in the southeast part, where the Atlantic Ocean, we get a lot of hurricanes. So this one is Hurricane Zeta, which is one of the largest US power outages in 2020. And I guess a lot of us remember several years before Hurricane Katrina. So, and hurricane is not the only one, which is a problem. There is a wildfire, right? And this year we had one of the longest wildfire in California and in the West. Again, that is something increasing every year, and one of the result of the climate change. It could be storm, like I said, like this one happened in Chicago area with the Con Edition, and several thousands customers out of power. And then most recent, last week, we had September 16, 21, Nicholas hurricane, which also resulted into power outage in Texas, and Hurricane Maria. And then there was snowstorm last year, actually this year in January in Texas, which resulted into a lot of power outages. Now, when these things happen, if we keep generating the power at a central location and transfer it for longer distances, once these kind of event hit, you cannot transfer the power because your lines and pole are damaged. But if we have more and more microgrid, it's obvious that we will be able to provide the power locally in a pockets, if not the whole grid. The thing is that can we reach out of microgrid and keep providing critical loads, because we cannot create microgrid because of cost for the whole grid, right? Although we do want to. So what does it mean that, and what we see, that electric power network is reliable, but not resilient. Now, why reliable? Because at least in the US, we have a 99.649, right? 99999% of reliability. We hardly lose power, for a couple of seconds in a year. So it is reliable in several different countries, and several, if not the whole country, but in part of the country is so reliable, but not resilient. And we are seeing it more and more as extreme events are increasing, right? So there are multiple reasons. Extreme weather event because of climate change is one. Infrastructure, which was built, several years before, several decades before, is aging. And then we also are seeing a lot of change in our grid, right? We have a more uncertainty of sources from PV and wind. And then we are seeing more and more control devices at the edge, which is called IoT in a smart city. So there is definitely a need. If I just look at last couple of years, there are extreme events happening, which is causing these problems, right, for the grid. So first, what is resilience? Because this is something that we do not agree as a group and define it. And
Sir, your voice is not coming.
Professor, please
yeah,
unmute.
I think for some reason it was muted. Now
Okay.
So here I was talking about that. What is resilience? And there is no standard for that, like reliability. And that's why we have a lot of definitions, right? So multiple definitions exist. And then, some agree that focus should be on critical load for distribution grid. And some say it should not be, because we should give importance to everyone. And out of all this definition, one that I like is resilience, the ability of the system to supply its critical loads, even in the presence of multiple contingencies. So because of the definition, there is no standard, there are a lot of working groups. So if you're familiar with IEEE, we have a technical council, and then within technical council, we have several different committees. Within the committees, we have several different subcommittees. And then within those subcommittee, we have several working group and several task force. And as far as I am aware, there is at least 5 different groups which are trying to work on these, define it, thinking about tools, including the one that I chair, which is on resilience tool. I was involved in several of those definition and metrics for resiliency. And then there is SIGRE, which is another largest organization in Europe. And there are several different groups like 4.47, 2.25, which is trying to define and come up with the definition and then what can be done and what we already are doing for this. Another definition is from FERC, which is ability to withstand and reduce the magnitude and a duration of extreme events, which include the capacity to, it all relies on how well we can anticipate the expected impact, how well we can absorb or withstand, and then how we can rapidly recover from such an event. So in this whole process, when using this definition that we just talked about, and you look at the power grid, we are putting more and more microgrids. Even sometimes we put mobile generators, and a lot of time we have this backup generator, which of course is not a mobile generator, but mobile generator is kind of backup generator, which can be moved at a certain location because you want to emphasize the priority of some loads. We're putting more and more sensors, and then of course this control is becoming more distributed slowly. It is not much in the field, but in terms of research, our control has become a lot distributed. So within the distribution network, we all know that we are slowly integrating more and more microgrids, right? Still the penetration will be, I would say, not even a 1%. If you look at the world level, but it's increasing over the years. And because of the microgrid, we have a microgrid management system that comes with that. Now, for extreme events, we would like to integrate a new tool in the control room, and especially in distribution control center. And we call it RTRMS, so Resilience Management System. So today, I'm more focusing on microgrid, even though advanced sensors, data analytics, machine learning based understanding of the grid and prediction is all of the work which is needed, and we have been working on that, and also distributed control. And how microgrid management system should interact with ADMS and RMS, which is resilience management system, to enhance our resiliency. So first thing is monitoring resilience. And as you can look at this chart, which is basically from one of our tools that we developed. We want to look at real-time resiliency number changing over time. And then we want to look at different factors, which is going to impact us resiliency. Now, these factors is something that not a standard, right? So we come up with our own factor, and then we integrate these factors which impact my resiliency with the same definition, the ability of the system to supply critical load. And then these resiliency is basically driven by these three things: my ability to anticipate, my ability to withstand, and restore. So what does it anticipate means? That how well the system is prepared for the predicted impact of an incoming event, right? And of course, it's before the event. During event, we want to know that how well we can tolerate or we can survive when the system hits. And then restore is something that we have been doing from long, which is restoration process. How quickly we can recover the system after the event is passed. Now, how quickly we can do it, it rely a lot on how well you know that how it's going to impact, and how you change your control and resources in such a way that you can withstand better. So another way, resiliency is a function of anticipate, withstand, and restore. And all of these need to be applied at different, basically phases of your system. So like I said, that before the event is anticipate, and before the event, you should be good. Your system should be operating in a blue sky operation, which is a normal operation. Black sky operation is the one when the event hits. So that is what withstand metric means. And gray sky means the event has gone, but your system is in compromised state or damaged state. So that's a gray sky. And all of these, anticipate, withstand, recover, will have, again, driven by that how well we can sense, how well we can harden our grid so that damage is going to be minimal. And before black sky hit, we need to do some proactive action, which means that you have to take some control action even before the event hit. Now that is totally driven by expected impact, right? And then restoration is again, like I said, that we have been doing it for long, restoration, even after fault or anything that isolates a part of the grid. So you can dip, you can go more deeper into all of these, and all of these anticipate, withstand, and restore, and find out that what are the key factor. For example, if I'm trying to do the anticipate metric, then I have to look at that what I know. So for example, I know that there's a warning for an event which is going to hit after a few hours. Typically we can do a good weather forecast, and then we know that what's going to happen next. Then we also know that how much crew I have and how many more personal I need to get. We know about your fuel reserve, we know about load profile, we know about battery if I have, and their state of charge. And then in terms of predict variables, we have a few things that I need to calculate or predict and estimate. For example, wind-induced failure, and then also inundation-induced failure, communication failure, launch risk. So all of these, and again, this is not a complete list, but something we need to predict because we cannot measure it, right? Here we can kind of measure it. Even though early warning is relying on the prediction, but we can still measure it in a better prediction mode. And in the same way, withstand, depends on your network, which is a topological factors. It should depend on your resources, that how much generation you have and where you have, either within the microgrid or outside the microgrid. And then it depends on your load location, which is your priority. Typically, hospitals will be your priority. Your city hall will be your priority. So a few things, your port should be priority. Your IT system should be priority. So all of those, we can take it. And then now we have a multiple factors, which is impacting my ability to supply critical load. And I will take those, anticipate and all those factors and come up with a single metric, which is, in this case, we are calling anticipate A, W, withstand, and then recover metric. And recover also, as we know, that depends on your network, your resources, and your load location. And of course, your control that goes with that. So we took all of these mathematical analysis and then, given a system, and we apply to multiple system in US, we can tell that if a specific event is going to hit, how well you are prepared to know the risk and impact on your system, right? So of course, this is even though we are working with the real system, but this one is kind of made up data. The reason is that no single, as far as I know, no single location will have all these kind of threat, right? I mean, tsunami, earthquake, launch, volcano will typically not exist together, except very few locations on Earth, right? So, but the point here is that we do know that what kind of threats are typically going to impact a specific region, and we want to know that how well we are prepared. So that's anticipate metric. Same thing we can do with stand metric, that if there are different scenario is going to happen against a specific threat, which I picked, like let's say tsunami, because I'm on the coast and I'm more worried about that. So now in a different scenario of our grid with like, let's say I have a 2 automatic switch versus 2 manual switch because the cost is different. I have a more battery, I have a more microgrid in the system. How my withstand is going to change. I can easily calculate that with that metric. And recover metric, this chart, which we probably have seen it before, that system is in normal condition, and then as the event progress, your system performance will go down, and then it will have some downtime before you start your recovery process, and then you slowly recover back to the same state, or you can, a little bit degraded state here because your resources are less. Now, all of these through control and through resources and through proper management, we can minimize this damage. We can minimize the state that you go to, and we can minimize the time to restore, and we can minimize the downtime, right? So with that objective, we can create again a multiple factor, which you already saw, for recover metrics. So one thing that I like to talk about, and we do have been working on multiple different tools to support this enabling resilience. And one of this tool is RMDT, and when we make these tools available to different grid operators with small changes, and then we have to call it different tools, but the core is same. Find the metrics for resilience, which we just talked about, anticipate, withstand, and recover, and then use those for basically to monitor resilience in real time, right? Now, if you talk about how do I enable resiliency at different timeline or time scale, there are different things that we can do, right? So long-term planning is typically grid hardening, which is like, like let's say Alaska, because they do get a lot of snow and ice, and if you put the cable outside, there will be weight of ice and snow, and it will be difficult to repair in very snowy weather. So you typically take those and put that underground, because it might be easier to first will have a less damage, but at the same time it will make it a little bit more difficult to repair, as you know that you have to dig in the ground and then fix it. But it definitely will take out a lot of threat related to snowstorms. So if you have more and more of those, you will do that. Now, underground cable will not help if you are flooded most of the time. So if you're in the flood zone, then it's not going to help. Point here is that one method will not going to work for all the different threats. Of course, vegetation management with the forest and everything, we need to, especially become more important with the wildfire. You can put a lot of more sensor, which we have been doing it as part of distribution automation. We can upgrade our poles infrastructure because it has aged out. We can put a lot of backup mobile generators, distributed optimization control at edge. Other thing is that when we apply any control technique, it has to run on one of the computing platform, and that should be also fault tolerant. So our computing should support it when it's needed. In medium term, which we should call proactive control before the event is going to hit, is estimating it right is important. Sometimes you have to segment your network in transmission and distribution. And with the microgrid, of course, when we connect the microgrid, typically it operates in grid connected mode. But with a temporary microgrid and with the advancement in polytronics, now we can even use grid forming inverter with proper control and computation to take as a microgrid controller. So those are temporary microgrids, which is just based on grid forming controller or inverters to form a temporary microgrids. Otherwise, be connected with the grid all the time. Moving generator and forming a ad hoc microgrid, which kind of goes with that. And then backup power, we have been again using from long time. More automation, switching, digitalization is also very important. Corrective control after the event, again, you can use the resources where it's needed, which is mobile generator. Doing a well-informed and proper decision. So you take out especially power to the critical load, not to all the loads. That's important. And then using all your automation and DR coordination. So microgrid with changing boundary is not only in the papers now. There are examples, like for example in Tennessee airport, Knoxville has a microgrid with changing boundary. And again, there's a reason for that, because you want to pick up critical load, which is outside your microgrid area, which was built in the past. So you want to change your boundary to pick that critical load, which was typically not needed in a normal operation, because it is not efficient to operate all the way through there. Network microgrid is again not very common in field, but a lot has been written in the research. I think we already talked about that. One control and one management technique and one measure that you can take is not the same for different events. So for flood, you have to do something else. For tsunami, you have to do differently. Avalanche, wildfire, storm, and the most important is cyber event, because the number has been increasing as high as the weather event is happening because of weather climate change, right? So cyber event is totally different because you cannot even guess, and anyone who's attacking your grid is hiding behind your all the monitoring system, because if they get caught, then most probably that event is not going to happen, right? Because you already stopped that. So cyber attackers will be hiding behind, and you cannot predict it. So there is no anticipation as such, even though something can be done in a hypothetical scenario, just like we do in post-mortem security of if this happens, what happens. Now, cyber attack, the way it's going to propagate into your network, you can try to predict it, but there are so many different paths and possibilities that it's not easy to do that. So anything that we are trying to do has to be custom designed for a threat, which we are trying to prepare our grid. So let me talk about some use cases. We talked about how to develop a metric which can measure resilience. We talked about how to enable it, some method. So now I'll talk about some use cases, combining all of these together. Now, we already talked about that resiliency objective is to maximize the supply to critical loads. And we can do two different kinds. One is proactive and one is corrective control. So in proactive, what we are trying to do is expect that where the event is going to hit, then also know the impact at which critical load will go out. And if you think about it, any component in the system, if it's live, if it is energized, and then get hit by the event, it will cause more problem to your grid compared to if that component which we expect to be taken out by the event, if we take it in advance, if we take out in advance, then the impact will not propagate in the system, right? Because you took out, and you all know that if you take out a component from the system, following a physics rule, that load on that line or that generator will be distributed among remaining line and generator. Now, you let it happen by its own, which will have more impact compared to you control it in advance, will have much less impact. So this is the idea behind this thing. We are looking at proactive control. And before the event is going to hit, and before we take out that line out, we have to do some shift and shed. Okay, what does it mean? That shifting the load from one feeder to another feeder, shifting the load from high load to a low load, because we can disconnect some of the load through a smart meter or some other component. Again, the idea is to minimize the outage of live component, and before we take it out, we want to shift and shed to minimize the impact. Now, when we do that, we can look at doing it in stepwise, right? Because again, you don't want a lot of dynamics in the system by switching. So we can use the distribution PMU based control for shifting and shedding it. And the way it is going to do is, which we'll talk about very soon, a little bit more detail. And then there are two more use cases that I'll talk quickly about that. So in shift and shed, given a system, we know that there's a storm coming and this is a path, right? And we know that because if this is a path, then this transformer will go out. If this transformer go out, then this part and there's another feeder So this transformer has 3 feeder, as you can see, from 1, then 2, and then 3. And all these becomes an island because it is all fed from here, from this side. So these 3 islands I can manage in such a way that it gets supplied from these 3 distributed generators or another feeder from here, which cannot pick up all 3 of these feeder, but can pick partial one. And again, our objective is to do that in a stepwise approach so that the dynamics is minimal. To do that, we look at, let's assume that there is a one line, which is basically in this case, and we have a DPMA here, and we slowly minimize the flow on this transformer before it gets out from the system because of this storm. So now we know that the flow on this transformer is basically proportional to the angle difference between these two, if we model it correctly. And then we want to minimize that angle difference slowly by shifting and shedding, right? So shift some of the load from here to this transformer and then shed some of the load so that these 3 generator can pick up the load, and at the same time only critical load. So we don't want to, so we want to shed some of the load which is not critical. And then I'm not going to detail because there are multiple papers which has been written, but here we again the whole concept is same, that shift and shed load, and which is proactive before the event is going to hit. And we are looking at DPMU data because we can measure the angle, and angle is directly related to the flow on that line, which is going to go out, or flow on the transformer, which is going to go out because of the impact. And we want to do it a stepwise approach to shed non-critical load and shift the whole feeder slowly. And each of this step is minimizing the flow on that line. That's what the goal is. So before the event hits, you go from 100 megawatt or 100 kilowatt, depending upon the system you're talking about, to make it closer to 0, the flow. So it become a non-live component. So as we can see now through the result, that we have a multiple resources which exist in the system, and algorithm that we just developed are being used or not, and we can minimize the critical load loss, right? So our focus is not all the load, because we don't have resources when these kind of event happens to supply all the load. So you have to focus somewhere, and we can minimize the critical load to 0 compared to what other kilowatt can happen. And that of course means the resiliency is highest in that scenario compared to any other scenario. AHP here means analytical hierarchical process, AHP, and this is one of the technique to assemble multiple different factors into a single number. So it's a multi-criteria decision-making process. There are several more. We have used AHP for all the factors that we just talked about. And also resiliency for different feeder can be changed. Now, these data is real data. This is from Idaho Falls, and we have also applied in Alaska. So use case 2 is a 2-stage proactive control with microgrid, where again, we have a system and we know that one of the area is going to go out, and now I need to create a multiple microgrid model. Again, assuming that we have thought about where the microgrid will be created, and we have thought about protection in advance, and we have thought about control. So all these things exist without a microgrid controller, because these are ad hoc microgrid. So without microgrid management system, which of course cost money, but here there is control exists at grid forming inverter to manage the microgrid when it's isolated. Now there are lots going on here. As you see that there is a database aggregator. Of course, we need to keep monitoring all the set of data. We need to have ADMS, which typically exists in most of the distribution system. Depending on the size, if it's very small, then ADMS may not exist, but there must be some control center or monitoring center for this distribution system. And then we have a resiliency management system that we developed, which is trying to find the estimate of pre-event threats, and then resiliency metric, which is AWR, and then proactive control to take. At the same time, a lot of time you have to send your crew. Now, idea here is you have a distribution system which has a lot of switch. Some are automatic, some are remotely operated, and some are manually operated. And if you look at the grid, even though we want to make it automatic, it costs us money. Or even remotely operated, it will cost more money. And in the past, we always had the one manually operated switches, which cost minimal money because it's not digitalized and smart. And in working with several different utilities, we still have almost 60 to 70% are still manually operated. So now, if it's a manually operated and you have to open that switch or close that switch for some reason because you want to do the restoration process before the event hits, then you need to send your crew to open and close, right? And that should be done like an hour ahead or 45 minutes ahead before the event hit, so that the crew can come home safe or to the office safe, because of course you don't want your crew to working on those switch when event hits. And then you have a switch which is remotely operated, which you can operate from the control, and then automatic will do its own job. So these three kind of switch, how do I use those switches in with normally close and close open switches to either close or open depending upon the event that is going to hit. And I want to maximize this, the load supplied, at the same time understanding the timeline of time needed by crew to open and close, and then understanding that there are some remotely operated switch. So this is applied to multiple systems. So this is, you already know, 123 bus system, which part of the grid is going to go out, this whole thing. That's where the path of let's say storm is, and this part will go out. And then I need to create microgrid 1, microgrid 2, microgrid 3, and then around this part I need to pick up somewhere, right? Because this that's where the power was being supplied, and if this goes out, then this all become without power, and I need to connect it to one of the nearby microgrid while shed some other load and keep supplying these loads. Another system is the Alaska system. So this is isolated microgrid system or islanded microgrid system in Alaska. We did a project. We have been there a couple of times, a very beautiful town. And that's where the Alaska Airlines started. And they got some hydro plant here. They got some hydro plant here in this place. And then several different DZ here and within the there. And then there's a battery, and then there is a storage, hydro storage plant too. So now we have to model this. So this is how the model look like, 45 node simplified model, not very detailed, because it still do the job. And I already talked about that there are the hydro, there are battery, and then there are diesel generators. So with that, our objective is to optimize my remotely operated switch and manually operated switch in such a way that we can do the two-step operation, first manually operated, And then stage 2 is remotely operated switch. So this is basically a restoration problem, but before the event is going to hit, so there is no outage happen, and it is done proactive. At the same time, it's optimization problem. So you can put your objective function, which is maximize the critical load, and then typically where we have in any restoration problem to take care of local generator capability limits, flow limits, and then of course your voltage constraint and power flow constraint, and we want to make sure that it's still radial, even though we can allow mesh, but protection does not support it. So we need to keep that in that way. And again, this is in paper, so I'll not go into detail, but I guess you are all smart enough to know that optimization problem is very typical of objective and a lot of constraint about the grid. And then we can clearly see from the result that if you have a different scenarios of event strikes upon the network without any preparation, and network is proactively configured, that's what we want to show is better. And then the third one is the outage part is operated through remote switches only minutes before. Now, the second one, as you can see, the scenario 2, it will give you the highest index, highest resiliency, right, compared to other two, which is expected because I prepared it and we solved the optimization with the proactive, and our estimation was right. Now, of course, estimation might be 80% right. In that case, it will be a little bit lower, but as well we can estimate and as well as we operate our grid, finally it will be better. Now, remember, looking at this, that just before the event, when the event is going to hit, it is a little bit lower than scenario 1. The reason is because in scenario 1, you don't shed your load when the event happens, right? You are only shedding the load in scenario 2 because you proactively reconfigure the system. So resiliency will go down during the event, actually before the event, because you took some load out. But that's okay because in long term, you get a lot of benefit. So last case is use case 3. And here, like we were talking earlier, that we want to use microgrid as an auxiliary resource to supply the power outside the microgrid. And in this case, we took a very small example of the, basically distribution system. And there is a DC microgrid. Of course, does not need to be DC. It could be AC microgrid also. And then you got your control inside the microgrid. You got the control at the system level, which is these two. And then you got the control at the ADMS level, which is basically here, controlling multiple feeders. Now, with all of these, what we want to look at is with the non-grid supportive mode and grid supportive mode. So non-grid supportive means that microgrid is operating on its own, and grid supportive mode means you can take the power out of the microgrid to support the grid activities. And then you can basically write multiple equation for where you want to take the power out, or you want for the voltage support or energy balancing. And then you can solve this problem of, again, optimization, just like we solve for the optimization for the other one. So with all of these, we need to know the daily load profile and, all the network details, all the resources details. And in this case, we are solving a problem of voltage within the limit, while microgrid is being used to supply the power outside to the distribution feeder. Other thing that once, as you saw that in all the 3 cases that we talked about, it's an optimization problem. And with that optimization problem, which we typically solve in a centralized way, can also be solved in a distributed way. And why? Because distributed, if you solve a distributed way, then you're also not relying on all the sensors sending data to the at the critical location, which is typically a distribution control center. And then the communication link and all the sensor needed to enable the centralized optimization might also be damaged with the event. So if that happens, then you will not be able to solve your centralized optimization. So distributed optimization and computing that goes with that to support distributed optimization is a little bit more robust, because if one part of the grid is gone in terms of computing and communication, it is still working. So that requires your decomposing the centralized optimization with a local power flow equation, local power flow constraint, and then some coordination between that, so you can get the similar kind of result. Not exactly centralized optimization, but very similar one. And we basically solve a couple of problems for restoration in distributed way, for voltage control, and this is something exciting field to work on. It's a challenging problem to guarantee convergence and with robustness, but a lot of work to do in this area. The other one is, of course, once you do the distributed optimization, then you need to think about how do I implement this in terms of computing. So we worked with Vanderbilt University, which made this REAPS node, which is designed for distributed computing. And also it can communicate with a neighboring node, and we demonstrated that it can work in real time. And these are our small microprocessor running these REAPS platform and running the distributed optimization interface with the RTDS and multiple sensor and controller. So all of these are based on, basically PMU actuator, and then Beagle board is that you see here. Right, so I will quickly show, like a 2-minute video. Let's change it to. So as you see here, we call it RTRMS, so the real-time resiliency management system, and it takes the system information. It has a resiliency monitoring that we talked about, AWR metrics, and then it has a decision support as shown here, and then also planning and analysis. So I'll not go into all the detail, but it shows you map as we go into the information for the system, which is loaded from ADMS or any other data sources. And then it should also know about the threat, which is what do you expect in future, and also how much we are prepared for that. That will be in planning part. So a lot of data here, and we have talked in terms of a little bit about this screen, which is showing the real-time monitoring of resiliency. Should change with time. And then with live map and weather, which will show you that what damage is expected. So let me stop on this one. I'll go to the last slide. So we talked about resiliency and then how microgrid can be used, which is again become optimization problem to supply the power inside the microgrid, which we always do that, but also outside the microgrid, and apply a proactive control before the event is going to hit. As we start from the use cases, the resiliency, the ability of a system to supply critical loads. Again, it's not a standard definition, but probably most appropriate one. It depends on the system characteristic, including network resources and control, and through coordinated control and planning and proactive control, we can maximize the resiliency, as again demonstrated from these use cases. All the control and planning we do should be specific to threat, and we need to understand the threat before we design these control technique to minimize the impact. A lot of time, these proactive optimal control you have to solve the optimization, which becomes, of course, challenging to solve with all the constraint. And especially if you want to make a distributed optimization, it's more challenging for convergence guarantee and robustness. So with that, thanks again to all the peer organizers and of course my research group, which do all the work, and several support from DOE, including UI Assist. Some part has been done with the UI Assist and the Radiance project. All right, I know that we have almost 5 minutes left for the questions.
Okay. Thank you, sir. That was really a value-added talk. I hope everyone has enjoyed this amazing presentation on microgrid as a resilience resource. Now, Professor Srivastava, we already have some questions that were sent to chat box. So we'll read out from the chat box. First question they have asked is by Prasant Jaina. Since it is impossible to anticipate a cyber attack in terms of time and location, how can we develop a resilient power system against cyber attacks? What are the possible solutions?
Yeah, excellent question. Now, we talked about anticipate, withstand, and restore, right? So you cannot put a lot of emphasis on anticipate because it's difficult to know that when it's what impact the cyber attack will have, because you don't know about it. But we can always put more and more on withstand, which is basically your IT OT security measure, make it more secure in terms of avoiding a cyber attack. And then recover aspect would be same, the one that we talked about. So knowing that how we can utilize our control and management of the grid as soon as possible after the damage or after the event has an impact on the grid is very important. So withstand, which is typically computer security, making it more robust, and then restore. All of these can be applied together to make it against cyber attack. And that's the only way, and that's the disadvantage we have, because we cannot prepare much.
Okay, sir, thank you. Second question is from Prasant Jaina. While simulating test system, how to identify critical loads, whether it is pre-decided or is identified based on any other factor?
Yeah, typically, and again, every utility was different, but the one that we worked with, they were pre-decided. They knew their area where they are supplying power, and they typically work with the city. City will have airport, like I said, that IT and hospitals. So these are all typically pre-decided. Now, if it's going to change during the event, because some specific event is going on in one of the building, then it's different. But typically, the one that we work with is pre-decided.
Okay, sir.
Yeah.
Sir, due to a time constraint, we will not be taking more questions. Okay, thank you, Professor Anurag Srivastava, sir, for answering these questions and for the great presentation. Unfortunately, because of time constraint and due to scheduled next session, we have not been able to take all the questions. I am sure participant will reach out to you for any further doubts or questions. It was a pleasure to have you with us. The talk was highly informative. I firmly believe that the talk will be instrumental in future learning as well. The knowledge participant will carry home from this session will help them in shaping their career too. As a symbol of our gratitude, we request you to accept a virtual token of appreciation.
Thank you.
So have a good day, sir.
Thank you so much. Yeah, and reach out to me. My email was there in the slide. So if you have more questions, thanks again.
Thanks a lot, sir. So now we'll be moving to our next scheduled session, that is panel discussion. So now we move to the last session of Para 21 workshop, that is the panel discussion on future perspective of microgrid. Before we start, let me explain how you can put your doubts to us during the panel discussion. If you have any questions or concern, please write us in the chat box. We'll take those questions at the end of the panel session. So without taking much of your time, permit us to introduce the panel member of today's discussion. So our first panel member of the panel discussion is Professor Vijay Vittal. Professor Vijay Vittal is the ERA A Fulton Chair Professor and Arizona State University Foundation Professor in Electrical Power System at ASU. Prior to ASU, Professor Vittal was an on distinguished professor at the Iowa State University, Electrical and Computer Engineering Department. In addition, Professor Vittal was a Murray and Ruth Harpole Professor and Director of the University Electric Power System Research Center and Director of National Science Foundation IUCRC Power System Engineering Research Center. He also served as the Program Director for the Power System for the National Science Foundation Division of Electrical and Communication System in Washington, D.C. from 1993 to 1994. He was the editor-in-chief of IEEE Transaction on Power System from 2005 to 2011. So now moving onwards, I have second panel member of today's discussion is Professor Ashok Kumar Pradhan. Professor Ashok Kumar Pradhan received the PhD degree in electrical engineering from Sambalpur University, India in 2001. He has been with the Department of Electrical Engineering, Indian Institute of Technology, Kharagpur, India since 2002, where he is currently a professor. He served at the Department of Electrical Engineering, VSS University of Technology, Burla, India from 1992 to 2002. His research interests include power system relaying and monitoring. Professor Pradhan is a fellow of Indian National Academy of Engineering and fellow of the Indian Academy of Science, Allahabad, India. Now, coming to our third panel member and moderator of this session, Professor Saikat Chakrabarti. Professor Saikat Chakrabarti completed his PhD degree in electrical engineering from Memorial University of Newfoundland, Canada in 2006. Before completing PhD, he worked in ABB Limited India and Bhava Atomic Research Center India. After completing PhD, he worked as a special scientist at the University of Cyprus and first as a research associate and then as lecturer at the Queensland University of Technology, Brisbane, Australia. Since 2009, he has been working in the Department of Electrical Engineering, IIT Kanpur, India, where he is currently a chair professor. Now, one small announcement. We would like to convey to everyone that Professor Abhijit Mahapatra will not be able to join the panel session due to unavoidable reason. He has expressed his sincere apology for the same. So, thank you, sir. Please, we can start the panel discussion for today's session.
Okay. Good morning, everybody. Very nice to see you all. Actually, it's good morning for me, but good evening for you all. It's about 5:30 in the morning here in Arizona. And Avinash had kind of given a very nice outline of what they would like us to discuss. So I have a short presentation. I would like to share my screen. Would you please allow me to share it, Avinash?
Yes, sir. Yes, sir.
Okay, very good. So this kind of addresses some of the points that Avinash had on his outline. And I just wanted to kind of talk about some of the key issues there. And I'm sure, Anurag would have addressed some of these. So one of the questions Avinash had asked was, how do active distribution networks and microgrids compare? And active distribution networks typically include significant amount of distributed energy resources together with storage, and that's the important part. And in emergencies, as a result of which these distribution circuits can be isolated, and as a result operated as a microgrid. And there are presently, in at least our state, Arizona, which is very solar rich, we have several distribution circuits which have significant DER penetration. However, there is still a dearth of distribution circuits which have enough storage to reliably operate as a microgrid. But there are some experimental setups where people have been trying to add storage and operate these distribution networks as a microgrid. And one of the things is, because the distribution circuits do have switching capability available. They have the ability to be switched between substation to substation. They also have the ability to be interconnected with other distribution networks to form a network distribution system. So multiple active distribution networks can be inherently interconnected to form a network grid. But however, this requires additional requirements for networked operation. That is, primary concern in the distribution network would be load generation balance, of course, requirements of maintaining nominal voltage and frequency, protection settings, and fault current capability. And when sufficient storage is not available in the microgrid, the ability to kind of reconnect seamlessly to the interconnected network must be enabled. Otherwise, you have problems. Then comes this question of hybrid AC-DC microgrids, and to a certain extent, this appears to be feasible only for newly developing or future planned development, because it's very difficult to retrofit an existing network to handle both AC and DC. There are some university campuses in the US where some of the modern buildings do have a separate DC network for computer labs and for lighting. And one of the important aspects here is you have to design this when the building is being planned. You cannot, it cannot be an afterthought. And there are many campuses which have significant rooftop PV. Our campus in Tempe has about 24.2 megawatts of rooftop on PV. And this is our basketball stadium. That's about half a megawatt. And then this is our rooftop with single axis tracking. We have several parking lots like this. This is one of the parking lots, and this is about 1.2 megawatts. So, that's how these things add up, and there are several campuses which operate as microgrids too. We have a separate campus, which is called the West Campus. It's our Polytechnic campus. And there are some experiments there going on to operate it as a microgrid independently, because they have several PV resources. They have a micro turbine also on that campus. Then one of the other questions Avinash had asked us was a T&D operation with mixed generation. And there are several examples now around the world showing the feasibility of operating fairly large systems with significant penetration of renewable resources in conventional interconnected systems. The good examples are, of course, Hawaii, which is the island, has significant solar penetration. California almost has 33% penetration through purely energy penetration of renewables, both wind and solar. Texas has a lot of wind. China has both the wind and solar. Ireland is dominated by wind, a very good example. Germany with a lot of solar. And then the UK, Australia, and of course in India, Tamil Nadu is an excellent example of highly efficient wind penetration in Tamil Nadu. So the question that needs to be addressed here, when you have such a large amount of non-conventional energy being pumped into the grid codes need to be appropriately set and adjusted to handle increased penetration of renewables. And this would include requirements on either grid forming inverters, appropriate storage, having active reserve, that is, you do not operate many of these renewable resources at maximum power point, but leave some kind of a headroom to allow for them to maneuver in case of need. There was one question Avinash had asked in his outline, whether it would be feasible to operate any system with 100% inverter interface generation. We have done some work in this particular area at ASU, and we have demonstrated this at least in simulation. So here, I have given you all reference to the 3 papers which kind of outline how we went about this, and it is possible to do that, and the system seems to work very, very well. But under the condition that you allow some of this to happen as shown on this particular slide. Then comes this question of what are some of the challenges when you have a T&D operation with mixed generation. Of course, stability and protection issues become critical to examine with high penetration of renewables. And Dr. Mukesh Nagpal has an excellent report on this particular topic developed by the Power System Relaying Committee. And this is the first document that actually came out in July 2020, and which talks about what are the challenges in protection. And I'm sure he addressed some of these in his talk. And then the Power System Dynamic Performance Committee has another report on how to define and classify stability related issues with the integration of inverter interfaced resources. And there was a similar effort which was done with a group of researchers in the US and in Europe. And we had a paper at the last PSCC, and you can access that online. So these kind of highlight what are the important issues. So now there comes this last question about the microgrid operation and microgrid performance. So I just wanted to highlight just the outstanding issues and what are the critical aspects that one needs to consider. So if you examine the microgrid, very similar to what Dr. Srivastava was talking earlier in his talk, it basically consists of a group of distributed energy resources and loads. The microgrid has clearly defined electrical boundaries, and is primarily a single controllable entity. And it operates either in a grid connected mode or in an islanded mode. So those are some key aspects to kind of realize. And this is a typical configuration. You could have multiple resources. It supplies a load. There are communication and control links. And if you examine the type of control which is required, the core functions of the microgrid control system is to maintain voltages, currents, and frequency, just like in any other system. But it has an additional complex problem of maintaining power supply and demand balanced. And this is because it does not have an interconnected capability to lean on the neighbor in terms of emergency. So the other aspect is you need to do this supply and balance, maintaining economic dispatch and demand side management. And you need to have flexibility to transition between modes of operation. So there's a very nice paper by a group of investigators in the IEEE transactions on smart grid, which basically define 3 control hierarchies for microgrids. Basically primary control, secondary control, and tertiary control. And if you look at microgrid stability, the key aspect of controlling stability in it is defined by primary control. How well you can do and how effective your primary control is. And what does primary control actually pertain to? It's primarily voltage and frequency control, the ability to share power and balance within the microgrid, and then to be able to very quickly detect that you are going to island and then transition to an island mode. So these are 3 very key factors. And in grid connected mode, you don't have to worry that much because voltage and frequency are mainly imposed on by the upper grid, and to a certain extent, you have some support from the upper grid there. But stability is mainly about individual or set of DERs and loads. And when you go into an islanded mode, voltage and frequency are maintained by DERs. And there are various stability issues depending upon whether you have grid forming units or not within the microgrid. So there is a very nice Power System Dynamic Performance Committee report on classifying and defining microgrid stability. And this is a very nice engineering definition of what is meant by a microgrid being stable. And all it says is that after being subjected to a disturbance, all the state variables recover to possibly new steady state values which satisfy the operating constraints without any involuntary load shedding. And there are certain criteria that need to be followed, and I have described what we mean by being in equilibrium, what is a disturbance, and then it can perform voluntary load shedding or disconnect loads to isolated faulted elements. And as a result of this, if you examine classifying stability in the microgrid, unlike an interconnected system, there are new classes of stability observed in microgrids. And some classical stability issues typically are not relevant. Example, rotor angle stability. There are not very many rotating machines in the microgrid. And instability in microgrid is primarily manifested by fluctuation in all system variables. And the classification that this working group has done in microgrids basically emphasizes the type of equipment and controllers involved, the physical cause, the size of the disturbance becomes very important, the time span of analysis, and the analysis method. And they have given this very nice chart, which basically classifies the stability. So there are two types of stability: control system problems, and the key problem here becomes power supply and balance stability. And then there are various different characterizations of phenomena within each one of these classes of stability. So in this table, basically, I have summarized what are some of the subcategories, the root cause, and how it manifests. So I'm sure Avinash will share these slides with you. I will not go into detail, but you can basically see this. So this kind of gives you an overview of what are the problems. And this particular topic that I mentioned here is actually available in another very good IEEE PSDP report. And this is actually, if you are a student member of PES, there is this very nice IEEE resource center, and you can actually download these reports for free. So this topic now has, and one of the key features of making microgrids feasible is actually implementing good grid codes. And this topic is of significant interest and debate in the community. And there are a number of issues related to both interconnected operation and islanded operation, but they basically pertain largely to maintaining load generation balance within the microgrid and the ability to control voltage and frequency. So with that, I will stop, and I will give the other participants a chance, and then we can go ahead with our discussion.
Thank you very much, Professor Vittal. I don't think there was
Hi,
any
Saikat.
better way to, hello, how are you?
Hi, thank you.
I don't think there was any better way to answer those questions in such a concise manner. So it just, for us to only add a few things to that possibly. Now, I'd like to request Professor Pradhan if he wants to add something to it.
Okay.
Then maybe we can open the floor.
Thank you, Professor Chakrabarti. Thanks, Para Committee and all to invite us. This is an opportunity and to learn in this presence. And special thanks to Professor Vittal encompassing all the perspective and so enriching slides and so many things, and then put all together in slides. Fine. So we'll go on. Let me say that summarize what we Professor Vittal has told the perspective of where and how to, what are the challenges and what are the things to be established and so and so. Microgrid concept is already established for last 10 years or so. This year, this Haiti earthquake killed 2,200 or more people, and the experience of microgrid is excellent. So microgrid technology and established technology, and now it becomes an essential and required thing. Now it has moved forward, so there is no going back or so. But then the essential things that how it can be incorporated into more and more into system. It should be affordable. The point here is that as already we know that so many deliberations and all these things are going on also, that resiliency, economical also from because of these things, we'll come to that, and then reliability, and then the carbon issues being addressed, and so the beauty of this technology is that local. The energy resource you are tapping is local. If you remember Gandhi's things about everything, I'm saying that gram swaraj kind of thing. So even something is not that cheaper, like brinjal you purchase from your own, you can say that village. That was the concept. So that does not require transportations and so that is environmental friendly and sustainable thing. And that is why we talk about microgrid is a sustainable thing because it is local. So we have resources like solar, resources like wind, biomass, even diesel, biodiesel, and all the perspective, whatever possible, that resources can be taken. Even small hydro also feasible here. The beauty here is that even if it is small, you can harness it. That was not possible earlier. So like we talk about in your own rooftop, you are having 1 kilowatt, less than 1 kilowatt, everything can indicate. And so that's where the local energy resources being tapped, that is the beauty, and that makes you can say that these things to be more viable and long-standing and also reliable. Now, there are so many things. I think Professor Saikat and his team, consider members also doing establish and all these things. I'll take some small things that things in the Indian perspective also. There are so many considered pilot projects in established things, both in DC and AC microgrid. But then the microgrid, you can say that it's emulating so many objectives, you can say that targets from the large scale grid or larger grid and so. Now, in case of Indian perspective, South Asia, you can say that there are a lot of issues and own challenges and all these things. The islands are, you can say that are very good. I would say that lands where the microgrid, you can say that scope is enormous. We call it chor also. There are a lot of chors in the West Bengal also. You can say that those are they don't have. You can say that they have to go by. You can say that boat also. May not be having bridges also. Now, in that case, if you think about a local microgrid may not be connected to the grid perspective. So in the Indian context, I think there are 2,400 plus kind of thing islands in South Asia and so. So the scope of, we can say that microgrid is enormous in this region. Furthermore, coming to this, addressing the issues of, we can say that Indian public and so, we call it mini grid or whatever grid you can say that. we have, you can say that enormous thing in the scope also. Like IIT Kharagpur is there, I'm saying that addressing a DST project, delivering 4,400 miniature, we can call it, we call micro solar dome. Okay? The concept here, you can say that is that we have already delivered to the marginalized people only. It is addressed to the marginalized people. 2,000, I'm saying that 25,000 or more than that, and target is in next 3-4 months we'll finish about 45,000. The concept there is direct sunlight. In the same, you can say that micro solar dome, direct sunlight, 6 watt of solar panel, 3 watt of LED lamp, and then you can say that it's charging unit where it is an embedded, you can say that battery, you can say that storage also. Through that, you can say that we can put a 3 watt of fan. We can have a 1 watt of, you can say that to the reading for the kids, and also we have mobile charging facility and all this thing. What do you find this beauty, like that IT thing I was telling? The beauty is that the devastations swept away all the solar panels in the eastern region when they have, I'm saying that 2 years back, you can say in the Odisha belt and so, 0 solar panel. So, however, because of these miniature things, and people took it away, you can say that from in advance, and because they were brought to the shelter and so, these miniaturized things were very resourceful, and they could charge their battery and light and all these things. So it was enormous help. So point here is that when you put solar panels, the devastation cannot ensure. When you put, you can say that even the big size wind farm also doubtful. Now then we can say that what will address to this devastation, for which you can say that we talk about the resiliency of the microgrid perspective and all these things. So these local resources, what capacity, what will address, all these things will be taken into, you can say that that one, because that is most highlighted thing in the resiliency perspective of the microgrid perspective and so. So I think we'll have more time, consider an opportunity, only less than 30 minutes. Let to consider more things consider emerge. So I'll join you consider. We have many more points we can address in the context of Indian perspective, global perspective, and so. And then comes against the interconnected microgrids and so what Professor Saikat and teams are doing a lot of work on that also. Thank you.
Thank you very much, Professor Pradhan. Maybe I will quickly highlight a few of our experiences that we came across when we were working on these microgrid related problems for last several years. See, one thing I'd like to mention that from the Indian context, there is actually a problem of adequacy in many parts of the distribution system. We don't have 24 hours power supply in many parts, especially in the villages. So when we were setting up as part of some project activities, for example, UI assist project, one idea actually came up. We were setting up some solar panels there in the village, and additionally we also had biomass installation. So then one idea came up, why not interconnect the adjacent hamlet also, or adjacent village also, because the power requirement in those individual hamlets or villages were not that much. The villages did not have many appliances. So from there actually the concept came whether we can try networking or electrically interconnecting these hamlets. And they can actually work as microgrid for a certain amount, for a period of the day, because those places don't usually have a 24 hours power supply. So they had to be designed in a manner that they can work off grid. So from there, this concept came up, if we can network those microgrids. So in fact, we then proposed one project, and we had partners from Canada and Australia also as part of Mission Innovation call. So there we had investigated this problem of network microgrid control operation and what could be the issues. The advantages are of course enormous. basically, given a limited amount of resource, you can actually increase the reliability of the supply there, because the demand is usually not very high in the villages. So even if the power goes off, given the limited generations that are there, we can actually make sure that those hamlets, interconnected hamlets, survive for a certain longer duration, or at least we can try to keep giving supply to the critical facilities like hospitals, schools, etc. So in a way, that was somehow increasing the resiliency of the network system. That was another objective. In doing that, we actually came up with another challenge, that protection challenges. We know that protection becomes very challenging when we have infeed from the other end. It becomes even more challenging when you have more number of PCCs and interconnections. It becomes a multi-directional power flow, and the coordination problems becomes a headache. So those are some of the challenges that we try to address. And yeah, and then coming to, just want to add one more thing here. When we get concerned when we're trying to replace these conventional generators with converter interface generators, very often people panic because we are losing inertia. Okay, so then we try to explore the positive side of it. We are losing inertia, which is true, but at the same time, we're actually gaining more controllability with the power electronic interface, and that control is much more faster than synchronous generator control. So that is something we try to explore. And interestingly, we saw that if we have, for example, those grid forming converters, then your system response in case of disturbances is actually in some cases better than having synchronous generators. So that was a surprise for us, and there was a new finding as well. So that is one experience we had. So yeah, I think that's all I wanted to add at the moment. And then I, in general, to the audience, and also Professor Vittal, Professor Pradhan, and if Anurag is there, to him also. One question I have, what about the cyber security problem in distribution system or microgrid? Is this perceived as a big challenge, cyber security in the distribution system, or we are looking into this problem only at the transmission level?
No, right now with increased penetration of rooftop PV and some large PV units, there's not as much communication interface as there is in the bulk system between energy resources and say some outside entity. But people are still worried about cybersecurity and some malicious players interacting with these energy resources. So there is some activity going on. There's a big push within the US DOE to actually incorporate cybersecurity right within some of these larger PV units and the way they communicate with the rest of the system. Okay. So there is some activity going on in that particular area, and quite a few research efforts in that particular area. It is a concern because, you know, if somebody can you know, fool around with your unit and do something to it, that could result in a problem. If you have do that to several units within the microgrid, that does become a problem. Yes, so that is an issue that needs to be addressed. Okay. But I think this point Professor Pradhan made, in India, this issue of a community microgrid and community solar does make a lot of sense. I've seen some examples of it in Tamil Nadu. There is a fairly isolated textile plant on a 138 kV system, and they have, you know, supply which is not very reliable. So they have basically created their own microgrid with a rooftop PV and biodiesel, and they very nicely combine both the biodiesel and the solar PV economically to basically run that textile. It's basically weaving and spinning machines when there is interruption of supply from the grid. So those are very concrete examples of where people could make good advantage of a microgrid setup to actually improve the quality of life in a rural setting.
Okay, so what Professor Vittal is saying, as I've already mentioned, there are varieties of scopes and I'm saying that scopes in the sense that hospital to community to storage in the sense of medicine store or grocery store to academics, or you can say that enormous. So all these you can say that require different levels of resiliency, reliability, investment they can afford, and so. In Indian context, you can say that we have all opportunities. You can say that whatever you do is considered fantastic at this moment. And for really, there is a dearth of electricity, and then the question is affordability, and so. On the questions we have raised, Professor Chakrabarti, that already addressed such microgrid, you can say that system. When you think about not grid connected. The grid connected means you can say that everything it can take from the grid side. When it is not grid connected, then the corresponding control protection are pretty rapid. Agree? So that's why control and protection, they have to go simultaneously. And that is so rapid, and then the backbone of this microgrid is communication system. So any interference through communication system will make this dual parallels. Agree? So therefore, you can say that cyber attack is possible. Even what do you say that the microgrid is not for residential, microgrid is for hospital, microgrid is for the army, you can say that locality, and so. Therefore, for critical, you can say that loads and load centers, this may create a problem also. And that's why Professor Vittal is saying that has also been that to be addressed in the controller, or you can say that in the corresponding protection arrangement. For that also it must be addressed. You can say that. That is what I see. Thank you.
Yeah, thank you. Anurag, can you say something?
Yeah, I mean, I'll just add that right now all these distribution network resources are kind of not managed by utility operator. So it's not tied into their cyber network, right? I mean, you cannot reach from solar at one of the house, their communication all the way till the to the distribution network. But as we install more and more utility operated solar, which could be like a community resources or within the microgrid, which is operated by the microgrid owner, then of course you can trace back your bytes from, basically from these facilities all the way till the utility control room. Then it will have more impact. But right now, I think as it's isolated network, and all of these digital devices does have a vulnerability. It does have a CVE, and because these are digital devices, but because we cannot trace back in terms of network, so the impact is very low, and that's why we don't hear a lot of those instances happening. Now, within the smaller system, which is a third-party owner, which is managing those resources, of course, we can impact, but not the system grid level operation. It is going to change or not, probably not, because of the privacy region. I think residential level resources will be still owned by someone else, not by the grid operator. But if grid is doing, operator is doing some community resources installation, then we'll have definitely a problem, because that will be tied with the operation center.
See, for example, our system here is 33 kV and not downtime. And now we'll have it, tomorrow will be microgrid. Most of the solar, and we have DG generator, and very likely tomorrow will be microgrid. Everybody is eager to that. Only have to add the required storage and so. And tomorrow that will be there. Now these, you can say that control devices, including protection, whatever microgrid control arrangements will be there. Now the existing relay and all these things, these will be now having the communication network because of this connectivity and so. So my point is that if you put any, you can say that such device, you can switch on and switch off those, you can say that devices easily. So the point what I think you are also perhaps agreeing to that the vulnerability scope will be higher in this case. If people connect, you can say that I have already considered communication systems and so I think.
So maybe we can open the floor to the audience now. Any question? There are some written questions written in the chat box. I would like to request other panelists also and Anurag also to have a look if you want to answer those.
So I think this question is about whether if there's excess power in a particular phase and the three phases are interconnected, whether it is possible to transfer to another phase. So this is, the three phases are somewhere connected simultaneously at a particular bus. And, this typically does happen in many distribution systems. We are actually working on a project on an actual distribution feeder within Phoenix, on the outskirts of Phoenix. It's purely residential, and on that feeder, when it is at 12.47 kV, and that is interconnected to a 69 kV system. So the most efficient solar production in Arizona occurs in the month of March and April. The temperatures are low and load is very low because the weather is very nice. We hardly use any air conditioning. So around 2 p.m. in the afternoon, somewhere between 2 to 4 p.m., this particular feeder actually feeds back 3 megawatts into the grid, reverse flow. So that's quite a lot of reverse flow for a feeder. So the question that somebody asked, there are most of these houses which have PV here have a bidirectional meter. So as a result of which if they produce excess, it flows back into the grid. And if somebody else uses it on the feeder itself, basically the utility buys back and their energy meter will have accounted for the usage of that excess flow. So yes, that can be done. That it automatically happens because of the way power flows, and there is no problem with sharing load between phases. I think that was one question which was there, right?
The other point is that perhaps, as I understood from this, if I have understood correctly, that if you have a controller in between, like a converter also, even if you are considered single phase, you can convert to 3-phase and so. So that flexibility that has, you can say that the converter has, even you can say that we are generating a resource of single phase also, you can convert to the 3-phase perspective or both the ways, bidirectional flexibility and so. But if you don't have, you can say that converter in between, then that will be considered maybe creating problem and so.
Any other question from the audience?
But I can put many things you can say that the discussion, the process Chakrabarti allows you can say that things.
Yeah, please.
Now, let us you can say that microgrid has come up to this. Now microgrid has a future. Now then, what are the bottlenecks in terms of availability of technology and so, and how we consider that will emerge and all this thing. I think Professor Srivastava is also there. That will be considered good things, perhaps you can say that. Like I can say that we require, as you are discussing, jointly, you consider optimizations, resource optimizations, interconnected, you can say microgrid or multi-microgrid systems will have a lot of, you can say that economically this and that. But one question which comes to me, I think Professor Srivastava and Professor Vittal can also say, see these interconnections when you talk about how much time they will deliver to each other. In case of urgency, yes, but that time is how much? Is it feasible in everywhere? Because most of the time they are grid connected. Then you can say that what is the scope? Only that they are either energy exporting or energy importing. So then they are selling, or you can say that they can, you can say that net metering they can do the grid also to the utilities and the supplier vendor. My question you can say that because query I have, you can say that sort of that if there are multi-macro grid and they have, you can say that we are talking about the connectivity and then economically viable and all these things, then the downtime, the urgency should be sufficiently high to dictate that economics, because we need a sophisticated technology to address that also. That is what I see. One scope, you can say that what I see from the interconnection of this multi-microgrid, what Professor Chakrabarti told about, is that resource-wise, suppose we have, if I have a, you can say that let us put a hospital critical load and putting a microgrid, then essentially requires storage, battery storage or so. Now, if one battery storage fails because of these connections, protections, connectivity, somewhere, some wire fails or something, then I must have to consider that this, you can say that 2 battery banks, you can say that at maybe different locations also with different connections to the grid at 2 points. Now, these you can say that the 10-1, something like comes into picture. If that resources can be optimized, if we have a network microgrid kind of thing, that is what I see. I think if we allow Professor Chakrabarti, then others can also tell about the genesis of that kind of thing and what kind of technology you can say that should further, so that it can be affordable and it can be reached to more and more people.
Now, one thing I can quickly add, I mean, interconnection is not actually an easy thing. One option is that you have a converter which remains connected all the time and you're controlling the flow. Other option is that you have switches, and then operating the switch very frequently is also not feasible. So I believe that, well, as of now, it's a bit of a futuristic scenario. But then even if it comes, I think it will be done only maybe a few times a day at the most, not more than that.
Yeah, I think all the decision. Oh,
Yeah.
Dr. Vittal, go ahead.
Go ahead.
Please, please.
Yeah, all this decision to interconnect and not to interconnect is you're right, and Dr. Pradhan, that it's in normal scenario, those are normally open and will be open, right? I mean, it's not needed to for those switches. But for not only resiliency, which is extreme event, even for reliability, which is typical fault that can happen in the system, that interconnection will help. Now, if you have resources in one microgrid, which is more than the load itself, then of course that extra power will help the neighboring microgrid if it is less resources. So there are multiple factors that need to be considered, because interconnection will cost money. It will lead to protection issues, right? Because your microgrid boundary is going to be now connected. So
no, my question was that how feasible it is economically to avail that interconnection, and so, because the interruption time, downtime is how much? That downtime will dictate the corresponding economics. That is what I am trying to say.
Yeah. No, but downtime is not only happening because of extreme event. It is happening
in the system side fault. System side fault also there is interruption. Yes. So then this
the biggest issue, though, Dr. Pradhan, in a microgrid is availability of energy in a given microgrid and maintaining balance between load and generation, like Anurag was saying. If there is a dearth of generation, and if some other microgrid consistently has extra generation, say a neighboring village.
Now, Professor Vittal, what I like to raise is that, yes, that is true, but that scope will remain unless, I'm saying that when there is no grid available.
Yeah, that's true. These are all realities in isolated systems. In the rural areas where there is no particular grid, but let us say one village has a gobar gas plant which is very efficient, and then a neighboring village does not have that capability, but this village can supply. So I think economies of scale do make an advantage as far as interconnection goes.
Off-grid, fantastic. This is very good to answer that.
Yeah. Off-grid. That's I am talking about only off-grid.
Yes. Okay, Professor Srivastava was telling something perhaps.
No, I was saying that like Saikat was saying that it's challenging, and it's the decision to connect or not to connect depends on multiple factors. So other than economics, normal operations should be taken care, and you are absolutely right that extreme event, which happens not very often, is not a driving factor for deciding the network microgrid or not.
The other point, Professor Chakrabarti, I was trying to say is that because this technology is not fully gone, Schneider, I'm sorry, that Alstom, these that they have already established their product at pockets of, you can say that these things, what I find from the literature, you can say on these things. True. Today morning, you can say that I was listening to a deliberations on the metering perspective in a national level debate. Very nice things was going on. Really, Indian context, how challenging, because now government has mandated that all, you can say that houses should be by certain time should be having a the metering should be ensured, you can say that smart meters should be ensured, and so, and it is promoting that for a sustainable distribution, electric market, and so sustainable things. What if the deliberation was that to the ministry, you can say that some of the I think Tata Power they are, and then I think South Bihar also they are doing that, and so. So they were asking that if you have a meter and that meter becomes faulty, then you have to replace a meter. This replacement of meter, it again requires a full complete arrangement, then it is not good. So therefore, this modular nature, you can say that should be also standardized, where the knot, bolt or screw has to be put. If that, you can say, does not have happened to, you can say, retrofitting, and so that becomes a cost affair. So that's what I like to say, that this microgrid and all these things, that there is a question also on the standardization and all these things perspective. If these things are, I'm sure that does not happen to be considered in the perspective of modular and interoperability, and then flexibility and all the perspective, and so then the progress will be considered that will be limited to only projects and so kind of thing. I think Prof. Saikat can coordinate in this.
Sure. Thank you. I think there is a question whether there is any example where implementation of multi-port network or interconnection is there. I think there is one example, right? The Illinois Institute of Technology has interconnected with its neighboring area, right? So that example.
Actually, many distribution networks, distribution feeders are primarily connected to a fairly large substation. Out of say a 69 kV substation, there could be 5 or 6 distribution feeders which go out. And as a result of which, if the 69 kV substation is disconnected from the rest of the system, and you have sufficient PV available on these distribution feeders and distributed resources, they can still operate in that particular fashion. So that naturally forms multiple microgrids interconnected with each other. And you can do the switching, because at least in the US, you can switch feeders between substations, because if supply is interrupted in one particular place, you can actually direct flow from some other place. So those examples do exist, but they are not natural microgrids, but inadvertently they become interconnected microgrids.
I think probably the question was about whether the microgrids are interconnected, not through the feeders.
I mean, that
somewhere down the line, whether they can have a PCC or whether they are connected. So I think
there are very less cases.
Well.
There are few examples of those.
Yeah. There is another question: how effective is the decentralized control of distributed energy resources?
Yeah, I guess it all depends on that, how we implement the control. And in terms of theoretical research showing that decentralized, you can, if you're trying to optimize, can you get the same accuracy as centralized? It has been shown. It is a lot of work need to be done, because in terms of practical aspect, to implement that kind of decentralized control or even distributed control, which is more challenging. But the algorithm use is going to decide that how good is decentralized or distributed control is going to be.
One thing possibly I can add here: it's more reliable than centralized. Even if the communication fails, it's going to work. So it's always desirable in that sense.
One more point I like to say, I think we are running close to our time of destination. So the point here is that where this is not happening, I was putting that questions. yes, economically viable at the transmission level, but here affordability is, you can say that economically not viable. Even though you can say that technology may be developed, but to put, you can say economically viable, that questions always come. Otherwise, the controls and all these things, what is being required at the transmission level, similar things we require to frequency control, the even if they are angle, maybe they are angle control, voltage control, all you can say perspective. And so the other questions at the beginning, it was mentioned about the DC and the AC. Everything is possible, but then you require converters and converters. Efficiency, investment, all the challenges are there. Those are all because we are harnessing local energy and all these things. Everything is free kind of thing. We can afford that if we don't bother about efficiency and so perspective and so. But then again, we always say about how the energy is being expended in terms of that and all these things. But Professor Vittal, at the beginning, we were telling about the India situation is now 40 plus 40 kind of thing for solar and wind. Now, if this 40-40 in a sunny day and good day comes all at a 80 for a, let us say, daytime, let us say around 150 gigawatt, then that becomes that it will really, for India, it will be too much, you can say, in terms of the renewable and all these things. So everybody is crazy, you can say that about 100% renewable. Let us hope we can say that we can realize in divided the higher voltage levels.
There are some questions in the chat box. I'd like to request all of you to see if you want to address that.
Frequency, yeah. I think Professor Vittal can say.
So I think frequency is not just the primary issue. Frequency occurs because, you know, the active power demand may not be met by the production. That's one aspect, but voltage also is an issue. But as you know, the others have mentioned, the critical part in the microgrid is also protection. I mean, how do you do protection in an economical fashion? I mean, you cannot have a widespread protection like you have in interconnected bulk system where any interruption comes at a very high cost. So I think you should have the right kind of protection in the needed places, and that becomes an issue of deciding how you provide that protection. Critical loads, for example, the example he gave about a particular hospital load or refrigeration of medicine in the hospital. So those are some critical factors in deciding how much protection and where you need it.
So tomorrow there will be classification of microgrids also, I believe. Depending upon the need, how much you can afford about the technology and all these things. True. Okay, I think 3 minutes time, I think anything, or if you have more time, we can move forward also, not a problem.
So any concluding remarks from the panelists?
I would like to thank the students for organizing Para. It's very nice to have interacted back with the institution where I got my master's. Very happy about it. And thank you for inviting me.
Yeah.
And thank you very much, Professor Vittal and Anurag, also for waking up so early in the morning.
Thank you.
And,
Yeah, really, it is very enriching. Particularly, I learned a lot instead of the deliberations and all these things. Fantastic. Yeah, it is very in this challenging time also. Thanks to the students' organizations, you can say that they have done a tremendous, commendable thing. Thank you.
we must thank the organization also. And in fact, I have seen that they actually manage things better than us.
Yes.
So thank you again, all of you. So Avinash, it's to you now.
Okay, sir. Thank you, sir. That was really a value-adding discussion and such an insightful contribution from each of the panel members. I hope everyone has enjoyed this amazing discussion. I would like to thanks to all the panel members, Professor Vittal, Professor Pradhan, Professor Saikat Chakrabarti, and Professor Srivastava for answering these questions during panel discussion and for the great presentation from Professor Vittal. I am sure participant will reach out to you and for any further doubts or questions they have. The panel discussion was highly informative. I firmly believe that this will be instrumental in future learning of the participant and it will help them in shaping their career too. As a symbol of our gratitude, we request Professor Vijay Vittal to accept a virtual token of appreciation from Para team.
Thank you very much. I really appreciate this.
Next, from the team Para, we would like to present a token of appreciation to Professor Ashok Pradhan sir. Please accept it.
Thank you so much. Oh, really happy to see it.
Okay. Now I request Professor Saikat Chakrabarti to accept a virtual token of appreciation from Para team.
Thank you.
With the permission of all the speakers, I would like to close this panel discussion session. Now we came to the end of Para 21 workshop. So I would like to invite Mr. Atul Kumar Soni, the Secretary of Para 2021, to deliver the vote of thanks. Over to you, Atul.
Thank you, Avinash. Respected professors, our most valued guests, ladies and gentlemen, it's my privilege to have been asked to propose a vote of thanks on this occasion. I, Atul Soni, on behalf of the entire Para 21 team, extend a very hearty vote of thanks to all the speakers for accepting our request and sharing your knowledge, your findings, and opinions with all of us. We learned about the concepts and challenges with renewable integration, digital energy transformation, the emerging challenges faced in the area of microgrids, hardware-in-loop simulation, project using real-time digital simulator, Typhoon Hill, Opal RT, etc. It takes a lot of effort to prepare and deliver a discourse. The organizing team is highly obliged to all the speakers. We are all inspired by your words. Further, a big and hearty thank you to our sponsors, Opal RT Technologies, Typhoon Hill, UI Assist, and IEEE UP section for sponsoring this fantastic event. Next, I express my sincere gratitude to IEEE IIT Kanpur student branch and IEEE UP section for their support. This event has been a significant achievement that cannot happen overnight. The wheels started rolling weeks ago. It requires planning and a bird's eye for details. We have been fortunate enough to be backed by a team of motivated and dedicated colleagues of IEEE PA's student branch chapter, IIT Kanpur, who know their jobs and are result-oriented. I acknowledge Dr. Ankush Sharma, the faculty coordinator of Para 21. Sir has always been there, providing his valuable guidance and mentorship towards the planning and execution of this event. A big up to my colleagues, the chair, Mr. Akhilesh Prakash Gupta, vice chair, Mr. Avinash Kumar, along with me, the secretary, Atul Soni, for inviting the speakers from all over the globe with the purpose of sharing practical knowledge. The treasurer, Mr. Viresh Patel and Amrendra Kumar for handling all the registration and financial related tasks. The technical program committee members, Mr. Gaurav Khare, Mr. Chamanlal Devangan, Mr. Arindam Mitra, and Ms. Anamika Tiwari for handling the online sessions responsibly. And Mr. Himanshu Gupta and Kinshuk Chatterjee for all the advertisements, banners, brochure, and poster related tasks. Any event is incomplete without its participants. We had 108 participants from approximately 30 different institutes, including IITs, NITs, universities, and private institutes in this workshop. I thank all the participants for joining us here. We will send you the participation certificate by next week on your registered email ID. The recordings and presentations of all the permitted sessions will also be shared with you very soon. I may also request you to kindly fill the feedback form circulated in the chat box so that we can improve the further Para events. Now I would like to request all of you to turn on your webcams so that we can take a group screenshot.
Hi, Atul. We have taken the
Yes.
screenshot.
Uh,
You can proceed further. We have taken the screenshot.
Okay, thank you, Akhilesh. So finally, I cannot thank everyone enough for their involvement and their willingness to take part in this event beyond their comfort zones. We thank you for being with us this evening. It has been a great pleasure. And with this, I close this ceremony. Thank you very much.
Thank you.
Thank you very
Thank
much.
Thank you.
Good night to you all. Bye.
Thank you.
Thank
See
you,
you,
sir.
Saikat.
See ya. Bye.